Good morning, my lovely 13s. Right, buddies, here we go on our next lesson on second order linear homogeneous constant coefficient differential equations, my buddies. How exciting! Cool. Now, my buddies, the title for this one is just auxiliary equations with purely imaginary roots. And just to let you guys know what's going to happen, we're going to finish the purely imaginary roots, but then we're also going to do complex roots today as well. So this note thing that I'm going to get you guys to look at right now, spoilers alert, will be presented in a couple more slides time in its complete and done format. So you might not want to copy it now, because I'm going to give you a chance to copy it in a sec. Cool, so here we go. As a recap, here's what we've done so far. If we had just a general second order differential equations, we discovered that the form of the equation was linked to what's called the auxiliary equation. The auxiliary equation comes from pretty much switching out the d squared y by dx squared with a lambda squared with dy dx with a lambda, and y is just a constant on its own. Now when we did that, here's what we discovered. If the discriminant was positive, we would have two solutions, lambda 1 and lambda 2, and this is what the general form looked like. Almost the same as the general form of the first order ones. So how exciting. And then the two lambda values just came from the two roots of the auxiliary equation. Same deal, well, not same deal. Secondly, we did it where we got a repeated root. So we got the discriminant equaling 0, and then we got this, a plus bx e to the lambda x. And whilst the bx kind of looks suspicious, last lesson we did kind of prove it still worked. So we did it in a roundabout way. We showed that the bx e to the lambda x did work as a complementary function, and it still gave the same answer. So here we go, my buddies. Next thing on the list is this. Shaboosh! What would happen if the discriminant was less than 0? In other words, we'd get out an imaginary number. Well, I'm going to tell you, it makes this, which you should write down. So you get p cos beta x plus q sine beta x. And you get that when the lambda is imaginary. Okay, so the solution from the auxiliary equation is imaginary. And we're going to call that beta, okay? When you get your lambda out, it's going to be like beta or beta, however you guys say it. It's going to be beta that is the one that is substituted in, okay? So whatever the answer was, you call it beta. Now, I'll tell you why in a sec why we're going to do that. But here we go. Are you ready? It's tricky to see why this one works, but it is cool. So I want to go through it with you. So let's do it. Cool. Right, buddies, let's derive it. So you might be thinking, yeah, that's all well and good. It is p cos beta x plus q sine beta x as well, but why is that the case? Why is it the case? Well, let's find out. Here we go. There's your general differential equation, right? But, my buddies, if we want this thing to be only pure or purely imaginary roots, so only imaginary roots, well, the b in this is going to have to be 0. And here's the reason why. Consider, because you know that we're about to swap lambdas in, right, and do the quadratic formula. Well, if you have a look, if we have b anything but 0, there's going to be a real part as well, because you're going to get the minus b over 2a's part if b is allowed to exist. So if we only want to have if we only have imaginary roots, then that means that the b has to be 0. So the equation we're going to solve is actually that. B has to be 0 if we're only going to get imaginary roots, which is what we want for this case. Cool beans, buddies? Sweet. Well, I bet you can do the next part, actually. The next part, then, is just getting what lambda would equal to. So let's do it. It's like a lambda squared plus c, which of course it is, because that's how that works. Move that over, minus c over a, and you square root both sides. Now, here's the problem. Well, it's not a problem for you, but here's a problem for most people, is you get a minus c over a, but you have a lambda squared equaling that. We got to square root both sides then, don't we, buddies? But the trouble being, or the trouble with that is, that we're going to get a complex number, right? You can't actually square root a negative, which would blow everyone else out the water. But you guys know, my buddies, already, that it just means that it's an imaginary number, right, buddies? So the square root of negative c over a is plus and minus as well, of course. And the square root of c over a, if it's negative, it's just going to be the square root of c over a times by I. So you have plus or minus root c over a times I. Now, C and A are both constants, my buddies, so let's give them a new letter, and let's call that letter beta. Okay, now we choose that, beta, beta, whatever. Oh, I'm so confused as to how to say beta now, because I say beta and I think you guys say beta. Oh, okay, so here we go. Anyway, beta is going to be the letter that we call that. You can call it whatever you want, really. Like, you could call it whatever letter you want, but beta is a sensible one, because remember, complex numbers always have like a real part, and then it's got the imaginary part with it. And typically, it's like the complex numbers are given the letter Z, and it's alpha plus beta I. Cool? So you may as well call it beta, because it is the thing touching the complex number, and now this matches up with the complex numbers you already know. Cool beans? Okay. Now, this actually is two solutions, right? Because it's plus n minus beta I, which means that we can use the form that we used when the discriminant was positive, which means we can use this form, right? The a e to the lambda 1x plus b e to the lambda 2x format, the same as when there was two solutions earlier. Cool? So that's what you wind up with. Now, my buddies, it's about to get exciting. This could be the final answer, but actually there's a better way of writing it, and here's what it is. You can use Euler's formula, my buddies, which is this: e to the I theta equals cos theta plus I sine theta. Now, I think you've learned this before. I'm 90% sure, because I spent a lot of time going through your textbook and checking what you knew, because I was a bit surprised when it just started popping these things out. I was like, do they actually know how to do this? And actually, indeed you do, which is so exciting, but I bet you've already learned it, so you're not going to be excited when I tell you about it. But I hope that you found this amazing. I hope you found this amazing when you learned it, because Euler's formula and then de Moivre's theorem, or whatever the hell it's called, is amazing as well, and they're both awesome in maths. Now, just to remind you, you don't have to do this for this question, but e to the I theta is cos theta plus I sine theta. It's really easy and cool to prove, and it's one of the most important results in all of maths, buddies. So I just wanted to quickly, if you wanted a bit of an exercise in proving stuff, you prove this, my buddies. Do you remember how to prove it? It's from the Maclaurin series, isn't it, my buddies? It's from these guys. If you take, right now, if you were to take the Maclaurin expansion, or you can get e to the I theta. It's this, my buddies. Well, here's the thing. These are like from your formula book. If you expanded the left-hand side of it, you could use this expansion, right, my buddies? Yeah, you could. And pretty much, because the i's will end up getting squared a whole bunch, like your i's will get squared, and then they'll turn into -1s, then when it's to the power of 4, it turns positive, and it's all that like weird stuff that I does, like the imaginary I. Since it does all that weird stuff, if you just do like a good whack of terms with e to the I pi in this expansion, you end up finding that if you group the I ones together, so some of them have I and some of them won't, if you group all of the I ones together, buddies, and you group all of the real ones together, then what you're going to find is that you actually get the sine and the cos expansions falling out of the e expansion, and that means, buddies, because you got them all written as expansions, e to the I pi actually equals this. If you haven't proved it already, but I suspect that you have when you learned this the first time, I'd suggest doing it, because you'll feel like an absolute boss if you get this right, and it's cool, it's really neat. Happy days? Anyway, we're going to use this, though, on these guys, so let's see. We're going to use that fact. Okay, so there it is, just written again, okay? E to the I pi equals cos theta plus I sine theta. That's the one, that's Euler's formula, so you know that now. But also, e to the negative I theta is cos theta take I sine theta. Now, there's lots of ways of proving this one, okay? This negative one, but I'm not going to prove it, but you should prove it. But it's nice and easy, though. It's also just from the Maclaurin series, okay? So if you were to do the expansion of the left-hand side, you would find that it makes cos theta and the sine theta expansion, but the sine ones are all negative. So you could do it the same way as you did the last one, but I like this. If you just actually use this one up here, this expansion, my buddies, well, what you'd find is your thetas are actually going to be negative thetas, so you'd end up with a cos of negative theta and a sine of negative theta. And I like this because it appeals to like the graphs, which makes it really cool. But cos of negative theta, so you get me, right? If I were to sub negative theta into the above formula, you'd get cos of negative theta here, but I'm just saying that's the same as regular cos of theta. Well, actually, yeah, it is. So if you imagine the graph of cos of theta in blue, then cos of negative theta is just a reflection over the y-axis. It's actually an even function, this one, so that means it's a perfect reflection on itself. So cos of negative theta does equal cos of theta. I've tried to draw it for you as a reflection over the y-axis. So you can see it, right? So actually, this is true. Now, remember how it was sine of negative theta? If you put negative theta into there, well, here's what I'm suggesting to you. Sine of negative theta is negative sine of theta. You can see that with the graph as well. So check it out. Blue is regular sine theta. So if it's negative, it's going to be a reflection over the y-axis. So this blue peak becomes this green peak, and so on and so on and so on. But get to your graph drawn, and once you finish your graph, you can see that actually a reflection over the y-axis is actually the same as a reflection over the x-axis in this case. That makes it called an odd function. I don't know if you have to know that or not, though. But it's cool though, so actually this is true too, and it's from the graphs, and that's another way of proving it. So how exciting anyway, so I stop going off on a tangent now and actually get down to this. Cool, I'm gonna get a wriggle on. Okay, which means, buddies, use your expansions that are just above, okay? So I've used the expansions of this, e to the beta I x, and that's just gonna make this. And the same deal with the negative one, it's gonna make that, and the a's and the b's are still touching, using the expansion, okay? Simplifies down just by getting the a's in and stuff, simplifies down to that. We're going to group the imaginary part and the real part. So the I ones are together on the right and the real ones are together on the left. I factorized in the same step as that because they both contain cos beta x. Can you see that? This one and that one went together. So I factorized the cos beta x, which gives b a plus b. And the same deal on the other one too. The I is common, and then I factorize sine beta x together, leaving a minus b. Cool? Now, a plus b is a constant, let it equal b. Q equals I, a minus b as well. It's just a constant too. It's an imaginary number, but it's just a constant too, which allows us to rewrite our thing like that, which is the general result. Cool? So we've done it. We've proved it. Hooray, how exciting. Happy days. Okay, this is the hardest part, the proving that I'm doing right now. The questions are not too bad. I'm going to show you. Okay, so first one that we're actually going to try. If you want to get ahead of me, please do feel free to do so. But let's work it out together. Are you ready, my buddies? Let's do it. Okay, it says this. Find the general solution of that differential equation. Well, my buddies, you're going to be absolutely beast at this. Let's do it. How do you do it? Well, the auxiliary equation for sure. This is just lambda squared plus 4 equals 0. So in other words, lambda squared equals negative 4. Which means lambda equals plus or minus the square root of negative 4. Happy days. And because you guys are sweet and know all about your imaginary numbers now, that means lambda is equal to plus or minus 2i. Happy days, buddies. So it's plus or minus 2i. So that's brilliant. That's what we've got. Plus or minus 2i. I made that really mucky now, though. Yeah, plus or minus 2i is what we've got. Now, that is purely imaginary. It's not a well, it is a complex number, but the alpha part of the complex number is 0, so it's only just imaginary, which means that we're going to go into our general form in a completely imaginary way. So here we go. It's going to be, oh golly, so it's x's and t's, unfortunately, in this one. So in this case, which is rubbish, I wish it was y's and x, but that's okay. X is the dependent one, okay? So our general solution is going to be this. It's going to be x equals, and it was, remember here it is, p cos beta x plus q sine beta x. So here we go. P cos beta, which is 2 x plus q sine 2x. Okay? The beta is the number that is touching the I. That is the beta. Okay, my buddies? Happy days? It's that one. It's not the I as well. It's only just the 2, okay? It's the coefficient of the imaginary part. Cool beans? Sick. Well, there you go. General solution. Bish bash bosh. No problem. Okay, a bit harder then. The particular solution, we got to actually just keep working with the general one. So it says x is 2 and dx dt is negative 2 and t is 0. So just go with each component individually. So t equals 0 has x equal 2. So let's do that component. So into the general, my buddies, it's 2 equals p cos, oh dear, these are t's actually, sorry I made a mistake, t, oh no, oh there, sorry, okay, these are t's, sorry my buddies, that's a t and that's a t, sorry, I'll fix now though, t, yeah, there you go, so this is going to be p cos of 0, and this is going to be plus q sine of 0, because we're putting t's or 0 in. So here we go, 2 equals, cos of 0 is 1, so this is just going to be p, and sine of 0 is nothing, so that means that p is 2. Happy days! Get the other one, get q, just by going the particular solution again, and let's do it. That one was t is 0, had dx dt equaling -2. Okay, so we got to differentiate the general solution first. So dx dt is going to equal, and let's do it. Sine differentiates to cos, so cos differentiates to negative sine. So this is going to be -2 from the chain rule, p, because it's chilling, sine of 2t. And this one here, sine differentiates to cos, so plus 2 from chain rule, q, because it's chilling, cos of 2t. And now let's whack it in. -2 equals -2 sine of 2t, so that's just going to be like 0, that whole thing, right? T is 0, and this one's going to be plus 2q and cos of 0. Cool. So you're going to get -2 equals cos of 0 is 1 is equal to 2q, which means q is -1. Which means, my buddies, we're ready for the particular solution. So the particular solution then is just then put in. Particular is going to be x equals p, which was 2 cos of 2t, and then q is -1 minus sine of 2t, and that's it. That answers part I. Happy? It's not too bad, is it? See, the proving it was hard, but we're not too hard here. Now, as I say that, I like part 3 a lot because it makes you really think. So part 3, buddies, it says this: find the period and the amplitude of the oscillations and sketch the graph of the particular solution. Oh my god, buddies, oh my god. Well, then, my folks, what are we gonna do? Well, here's what you got to do, my buddies. It's not really nice to draw this graph. It's a bit of a nightmare. So, do you know a trig scale from regular? I'm going to change colors as well so you can see. Do you know a trig scale from regular A-level maths that would help you sort this out? That's right, buddies. You don't want to have two separate ones. We're going to combine the sine and the cos as one. So let's do it. It's going to be that like a plus blah 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 thing. So here we go, buddies. I'll show you what I mean. So you go like this. You go 2 cos of 2t, take sine of 2t, and you're going to use this weird thing here. Do you remember this? Do you remember the r sine? And check it out. 2t plus alpha. Do you remember that format, my buddies? That compound angle formula stuff. Yeah, or sorry, we'll use the compound angle formula, but you're able to write a sine and a cos together. It can be combined as one or the other. You can equally do this for cos all you want, but yeah, that's what we're going to be left with. So check it out. What do you get on the right-hand side? Well, let's compound angle formula it up. Sine, I think, is this one. I think it's in the formula book, but it's going to be this. It's sine cos plus cosine, I'm pretty sure. So it's going to be r sine of 2t cos alpha plus r cos of 2t sine alpha. Now, I kind of wish I had at the moment cut and paste the thingies from the formula book, but that's one of the compound angle formulas. Cool beans? Okay, sweet. So, yeah, let's do it, my buddies. Let's do it. So, now we can compare each side, okay? So if you compare each side, let's just make sure we're clear on this. Let's do it. Okay, I'm going to equate on the cos of 2t's, of cos of 2t. Now, if you equate on cos of 2t, the left-hand side has got 2, and the right-hand side is going to be this second term. It's going to be r sine alpha, which means that sine alpha is equal to 2 over r. Cool? Now, if you equate then on sine of 2t, sine of 2t. Oh gosh, I'm going to get a negative nightmare. If we equate on sine of 2t, here's what we're going to find. We are going to find that we've got on the left -1, and on the right we are going to get r sine of 2t, r of cos alpha, which means that alpha is going to be, or cos alpha I should say, cos alpha is going to be -1 over r. Cos alpha is equal to -1 over r. So what is our next step, my buddies? What is our next step? Well, we're going to have to actually draw out a bit of a picture, my buddies, for it. That is the next step. Now, I am a little bit surprised that this came out negative, I'm not going to lie, but it won't phase us, it's okay. Usually you just draw a triangle now, buddies, with alpha in it, like a right-angled triangle, but because it's come out negative, unfortunately, I've got to kind of cast diagram it. Sorry. I should have picked the cos one potentially instead of the sine one. That's okay though. It doesn't phase us, my buddies. And here we go. Here we go. So sine is positive, right? Sex and the city or cast. Okay, sine is positive and cos is negative. Where does that happen? Well, here. Cool. That's the quadrant that has sine is positive and cos is negative. And I'll show you, my buddies, it's cool. Go like this, stick into this quadrant, and now you can see why it's the case, okay? That can be our alpha. It's actually going to be bigger than that, but that's okay. We're going to use this as the alpha for now. Sine of alpha was 2 over r, and cos of alpha was -1 over r, and now you can really see, can't you? That's why that's negative, buddies. That's why it had to be in this quadrant, because the negative to show it's going left. Cool. Well, there you go. Let's get r then. So let's get r's Pythagoras' theorem because it's a right-angled triangle. So let's do it. So r is going to be the square root of 2 squared plus -1 squared. So it's √5. Cool. And then you're also going to get the other one as well. Let's go tan of alpha. And if we do tan of alpha, you're going to get 2 over -1. And I'm going to actually put the negative in and hope it just gives me the obtuse angle. I hope it will. I think it will. If it goes negative, we're going to have to fiddle. But I hope it will. Okay, here we go. I'm going to switch to radians, okay? Because this should probably be radians I'd have imagined. So mode, Boudrat, setup. 4 for radians. Here we go. Okay, shift tan of -2 equals negative, whatever, that's okay. Negative 1.107. Negative 1.107. 107. It's going to give the same answer. I'm going to obtuse angle anyway. So I'm just going to bosh it in. I'm going to just ignore that it's negative and I'm going to bosh it in because it still is going to work, my buddies. So you ready? That means this entire thing, this part here, is actually the same as this. It's actually the same as √5, open bracket, √5 sine, open sine, sine of 2t minus 1.107 in radians. Now, there you go. That's it in the format of one particular thing. So whatever. Yeah, this is it in the yeah, this is it, drawn, my buddies. Cool. Now, that's it. That's in a format that you can actually read the period and the amplitude and stuff off. So let's answer the question, and then we can sketch it if we want. Find the period and the amplitude of the oscillations. Okay, so straight away, you ready? Period's going to be this. Period. Well, normally, sine has a period of 2 pi, right? So in this case, it's going to be 2 pi, but there's a factor of 2 in there. That's what's affecting the period, okay? It's got a horizontal compression by scale factor 2. It's a horizontal squeeze by factor 2. So you divide by 2. Cool? Which means the period now, my buddies, is pi. Okay? Happy days. Now, the other thing that we got to do as well is what is the amplitude? Well, that one's the easy one. The amplitude, well, sine usually goes between 1 and -1. So now that there is a √5 touching it, it's just going to be a vertical stretch by that. So the amplitude, my buddies, is just √5. And that answers that question too. Now, it does say sketch it, but I I kind of don't want to, but I know. I'm going to put it onto autograph for you. Okay, it is easy to sketch though, okay, just to show you. This is easy to sketch. And here's the reason why it's easy to sketch, because what you're going to do is it's going to go up to root 5, down to minus root 5. Oh, what the heck? I'm just going to draw it. I'm not going to use autograph. Okay, it's going to be really sloppy. You should try to draw it as well. Okay, so here we go. Our sine graph is going to sketch up to root 5 and down to minus root 5. I'm going to try to be quick. Okay, so what are we going to go? 1, 2, 3, 4, 5, 6, 7, 8. And let's do it. So we're going to be having here, okay, pi over, no, I'm not going to label them all. Let's label every second one. So we're going to get pi, 2 pi, no, because I'm going to have to half. Oh, see, I told you it's a fiddle to draw. Okay, let's draw the normal range. Okay, it's pi over 2, so I'm going to put pi over 2 here. Okay, this is pi, so I'm going to skip 1 and put pi there. I'm going to skip 1 and put 3 pi over 2 here. And I'm going to skip 1 and put 2 pi here. Yeah, that's probably the way forward. Okay, now here's what you're going to do, my buddies. It should, it's going to be tricky to draw. Sine just with the compression in it, the horizontal stretch in it, it's going to be like this, okay? It's going to be like, without shifting it, it's going to be like this, and finishing at pi, and then going again. Okay, so it's going to be like that, okay? That's what it's going to look like. And then the next shift, which, oh, here we go. The next shift is 1.107 radians. So what's pi divided by 2? 3.14 divided by 2. Okay, is 1.57. So it's shifted to the right by not quite that amount. So it's as though it's going to start here first of all, and then here second of all. So it's just fiddly, my lovelies. Essentially it's this, but shifted over like that, my buddies. Okay, so it's the purple one, but shifted correctly rather than what I'm doing. Cool. You can see that by moving each point. So if you wanted to do it accurately, you'd have to move the points on the top as well. Yeah, cool beans. Okay, final thing I'm going to show you, my buddies, is, because it's not, I'm going to do a long video today, a short video next time, check it out. This is complete now, okay? So pause it and take a note. The final thing for complex roots is that one. So there you go, my lovelies. Okie doke. So this is it for complex roots. The final one, in other words, you're going to get, if you've got a negative discriminant, but it is complex as opposed to only just purely imaginary, it's going to have an e to the alpha x in front of it, and that's it. Okay? Pause the video and write that. This is complete. So put it somewhere safe and somewhere convenient that you can refer to them if you need to. That's it. You finish the course on this. Okay? So this is all of the options. Cool. So now let's do it. The bottom one, where does that formula come from? E to the alpha x, blah, 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 like that. P cos beta x plus q sine beta x. So it is the complex part, or sorry, it's the imaginary part, but it's also got the real part, so it's a complex number, and it's for this scenario. Well, let's check it. Let's find out why. Okay, quick derivation. If you're to go through it, my buddies, you're going to get that. Okay, so here it is in general. Here it is figuring out lambda, and all I've done is I've split it off into two parts, the part with the b and the part with the square root. But I want it that the square root part is negative, okay, so I'm going for it, the square root part being imaginary, and now all I'm going to do is invent some constants. Minus b over 2a may as well be alpha, and then the entire part, b squared minus 4ac over 2a, but with the I pulled out, may as well be beta, which means we're going to be which means that we're going to be left with this. So all I've done is switched everything into a constant, alpha plus or minus beta I. Happy days? I hope it's okay. So I've skipped a lot of steps here because I knew this video was going to be long. Oh, I did know it. So hopefully that's okay. And you get why that is, okay? Minus b over 2a is alpha. And the entire part that you can see there, apart from the I that's going to come out because the discriminant is negative, is beta. Cool. General solution then is this. And it's got two, because it has two solutions, right? This is two solutions, therefore we can use the positive discriminant format. Cool. which simplifies to that when you break it down with the index laws. Yeah? Which simplifies to that when you factorize out an e to the alpha x, which is common. Now, my buddies, can you see that inside you have a e to the beta ix plus b e to the negative beta ix? Can you spot this bracket is the same as the purely imaginary one? So here we go. Check it. Ready, buddies? See the screen right now? Shabang! There! Can you see this? It's the same as this one. A e to the beta ix plus b e to the negative beta ix. Whew! There you go, my buddies. Can you see that that's the same as this? Therefore, this part is just the purely imaginary part, which means it's that. Bang. Now, there you go. This is the final thing, where this alpha is the real part of the root, and this beta is the part that's touching the imaginary number. It's the coefficient of the imaginary part, okay? It's the coefficient for the imaginary part. Cool. Feel good, buddies? You know how to do it all now. How exciting. This is it. Okay, final thing, then I'm going to set you off to just do a few questions. It's not a big lesson today. You're getting a big, well, it is a big lesson, but it's not a big practice lesson for you. It's a big lesson for me and not for you today. Oh, okay, so let's do it. Find the particular solution to this differential equation which satisfies these initial conditions. Cool. Now, I'll betcha you probably don't need me. I'll bet you don't. So my challenge to you is pause, go. And if you wanted to do it with me, here we go. Let's try it, buddies. Let's do it. Okay, so first things first, auxiliary equation, aux. So lambda squared plus 2 lambda plus 5 equals 0. It doesn't work. There's no two numbers that times to 5 and add to 2. So here we go. Lambda equals -2 plus or minus the square root of 2 squared minus 4 times 1 times 5. Cool, all over 2a, all over 2 times 1. So lambda is -2 plus or minus the square root of, this is going to be 4, take 20, all over 2, which means that lambda is -2 plus or minus the square root of -16, all over 2, which means that lambda is -2 plus or minus, now negative is going to make an I, the square root of 16 is 4, 4i, all over 2, divide them both by 2 because they all go into 2. This is -1 plus or minus 2i is your root there. So what you spot is that you've got a complex root, okay? Not an imaginary only root, but a complex root. So, just so you remember, this part here, buddies, the -1, well, that's the alpha, because it's literally following this format that you guys established in the complex number sections that you've done, and that means that beta is just 2. Cool? Right, we'll pop in your general form then, so let's do it. General form. General form then is going to be this. The general form is going to be, it's going to be its y's and its x's, which is good. So y equals, and it's e to the alpha x, e to the negative x, okay? And then it's going to be p cos beta x, so p cos 2x plus q sine of 2x. 2x. And bang, there you go, general form done. Happy days. All we were doing was using this exact formula, this exact form that you're used to, p cos plus q sine, and there's an alpha in it. So there's what we've got as our general solution, which is cool, so that's really important. And now we're ready to go for the particular, because it was about particular. Okay, for the particular then, you just use your conditions. X equals 0 has y equals 0, which means we're going to get 0, because y is 0, equals e to the 0, and it's going to be p cos of 0 plus q sine of 0. Okay, oops, not e to 0. E to the 0 is just 1. And the sine of 0 is 0. So we're going to get 0 equals, and it's going to be 1 times, well, it's just going to be p from there, because this is just 1, and that's going to be 0. So actually, p is 0. How exciting. P is 0. Cool. To use the other condition that we're gonna have to differentiate first. So we're gonna use the x is 0 and dy dx. Dy dx is 1. So let's use that condition. So Oh golly, yeah, here we go. Here we go. It's gonna be some chain rule going on here. How exciting. I'm gonna be lazy. I'm sorry, I'm doing it. I'm being lazy again. Okay. Right, buddies, because I can't really be bothered, I know that P is 0, right? That's a huge hint to me, okay? So because P is 0, I don't want to have to chain rule or product rule twice on this. So P is 0, so let's cut to the chase. The general term is already not having the P in it, yeah? So actually the general term is QE to the minus x sine of 2x. I'm just being lazy. I could differentiate this whole thing, but P is 0, right? So I may as well just bin off that term. That's what I reckon. Because now we only have to product rule one time, so I've just binned off the P part because I knew that it was 0. So let's do it. dy dx. And here we go. It's going to be, differentiate the first part, it's going to be minus QE to the minus x, chill the second part, sine of 2x. Cool, plus, leave the first part, QE to the minus x, sine difference, so that's this part chilling, and sine of 2x is going to, sine differentiates to cos, so this is going to be cos of 2x, and chain rule is going to have the 2. So there's what you're going to get with that. Now we're ready for our initial condition then. So dy dx is equal to 1, and x is equal to 0, so the sine part's going to go, the whole first one's going to go, and you're going to be left with 2q e to the 0 cos of 0. Okay, cos of 0 is 1, e to the 0 is 1, 1 equals 2q, q is a half. Cool, which means we can do it. Our final answer then, the particular solution, is this. The particular solution is just then bodged in. So here we go. Y equals e to the minus, actually, yeah, no, I'm not, yeah, I'm going to do, here, I'm going to show you what I'm doing. I'm being a step skipper, that's what I'm being. I'm going to use this one as my general solution, so I'm going to put into that, because I already know that P was 0, so I'm saving myself a writing. So here we go. It's going to be a half, oops, a half, okay, it's going to be a half e to the minus x sine of 2x. Like a boss, y equals. And there you have it. There's your general solution, my buddies. I hope you feel good about that. I hope you see it's not too bad, actually. It's nice that you finished everything because now I can give you tons and tons of practice to do. Please don't go super hard straight away, okay? Because I'm going to do a whole other lesson on you for hard ones. So 273, question 1 to 4. I said try for all, but I didn't realize the video was nearly going to be 40 minutes. So if you just try, make sure you've got excellent notes from this video and do your best to try a couple of these if you could, okay? 1 to 4. Don't go past 4 yet because they go a little bit harder and I want to help you before you do the hard ones. Cool? So maybe question 1 and yeah, see where you get to. Happy days, buddies? Whew, okay, well that's it for me then, my folks, and I shall see you next time. Bye, buddies!